Hey everyone, here's your lesson for Friday, May 22nd. Okay, today we're going to talk about applications of quadratic equations. Basically what that means is you're going to be able to apply quadratic equations to the real world and see where these come to life. So first off, let's just review a little bit. Okay, Yolanda and Daryl compare key features of the graphs of two quadratic functions. So we have d of t and h of t, and we see them here. Okay? They seem to disagree on interpreting the point of intersection. Yolanda claims a point of intersection represents a minimum, whereas Daryl claims the point is a maximum. Describe why they are both correct. Well, if we look, okay, for this graph, well, first of all, here's the intersection point. For the graph of h of t, this is a minimum, and for the graph of d of t, it's a maximum. So, the point of intersection for h of t is a minimum, and for d of t, it's a maximum. Explain how Yolanda and Daryl can represent whether a quadratic function has a maximum or a minimum without graphing. Okay, we learn this. Remember, we look at the leading coefficients. So if we look at the leading coefficient of d of t, it's negative. Okay, if we look at the leading coefficient of h of t, it's positive. So negative coefficients, okay, have a maximum, whereas positive coefficients have a minimum. So I'm going to say if a, and remember, a is the leading coefficients. Okay, if a is positive, it's a minimum. If a is negative, it's a maximum. Okay, so basically a would be positive or a would be negative. Alright, first problem here. We're just going to do two problems today, guys, and that's going to be it. Alright, number one. A ball is thrown into the air from the edge of a 48-foot high cliff so that it eventually lands on the ground. The graph below shows the height y of the ball from the ground after x seconds. So, it starts at 48 feet. We can see that here. The ball is starting at 48 feet. The graph below shows the height y, so let's label our graph. The height is our y-axis, right? And time is our x-axis, seconds. Or actually, I'll keep consistent here. I'll just put seconds is our x. Okay, I'm just taking that right from here. Height is y. The x is seconds. So, part A. What does the domain represent? Okay, remember, domain stands for x. Well, the domain, simple. Domain represents seconds. The x-axis represents seconds. What does the range represent? The range is y. So the range, the y-axis, represents the height. C. What is the context of the problem? So it's just asking you to write a sentence about what's happening in this graph. What is the problem trying to explain to us that's happening? So what's happening, okay? A ball is being thrown off a cliff, and we're looking at height over seconds. So a ball's height over X amount of seconds. C, over what interval is the height of the ball increasing? So what interval is the height of the ball increasing? So we're looking at height. So we're looking at the y-axis. Okay? Well, the ball seems to be increasing until we get to about here. Okay, so it starts at 0 seconds, right? And it goes to, so 0 seconds, and it goes to about 2.5 seconds. So we go from 0 to 2.5. Over what interval is the height of the ball decreasing? So now we want what interval is the height of the ball decreasing. So if I'm looking at decreasing height, I'm actually starting to decrease at 2.5. So 2.5, x is between 2.5 and it finally comes to a stop at about 5.5. Okay, that's it. Let's look at another one. 2. Sheila tossed a ball in the air in such a way that the path of the ball was modeled by the equation f of x equals negative x squared plus 6x plus 7. In the equation, f of x represents the height of the ball in feet, and x is the time in seconds. So f of x represents the height in feet, and x is the time in seconds. So I'm going to label that here on my chart. Okay, so x is time, and f of x represents the height in feet. Remember, f of x is just the same as y. Whenever you see something that looks like that, g of x, t of x, with the parentheses, it's really just referencing y. So, it says, what is the context of the problem? Okay, well, she's tossing a ball in the air. So we're looking at a ball in the air over a certain amount of time. It's just a sentence. You really can't go wrong. You're just describing what's happening. Part B. For how many seconds will the ball be in the air? Well, in order to answer this, we have to get some numbers here. We either have to take our equation and put it in GeoGebra and look at the graph, or we could use the table of values. So we're going to do both. So let's put the equation into GeoGebra. Okay, we have f of x equals negative x squared plus 6x plus 7. Enter. Okay, we get this really giant graph here. But really, we just want this piece here. We just need the piece where we have all the positive x and y values. Okay, so what I'm going to do is I'm going to put into my table from x equals 0 to about 7. So I'm going to look at my table of values for x equals 0 to 7. Okay, and I'm going to copy those table of values into my work area. We had 1, 2, 3, oops, sorry. I want to start with 0. 0, 1, 2, 3, 4, 5, 6, 7. And the other side of the table was 7, 12, 15, 16, 15, 12, 7, 0. Okay, and again, we talked about this in the last lesson. Look at the turning point here. Okay, look at all the y values, the f of x values, and you can see that the turning point is right here, right? We're at 16, and we have an identical mirror image of each other with the values, okay? So part B, for how many seconds will the ball be in the air? Okay, well, time is x, right? So how many seconds total is the ball in the air? And you can see it on the graph. Well, the ball is in the air for 7 seconds. The x-axis is 7. And if you want to draw yourself a little chart here, here's my X and my Y. You have your seconds, or your time, and you have feet. And it kind of looks something like this, right? The ball is in the air for 0 to 7 seconds. So we write 7 seconds. C. What is the vertex of the quadratic equation? So either the minimum or the maximum, right? The point of where it reaches its max. In this case, it's a maximum because it looks like a mountain. So the point where it reaches its maximum height is 316. And also, you notice it's the same turning point here, 316. State what the coordinates of the vertex mean in the context of the problem. Well, 3 is time in seconds, right? And 16 represents feet. So we're just writing a sentence that uses those numbers and those words. Okay? So at 3 seconds, the ball is 16 feet in the air. And that's it. D, what is the y-intercept and what does it mean in the context of the problem? Alright, well, let's go back. The y-intercept, where this graph crosses the y-axis, which is right here. Okay, so it crosses at y equals 7. So y equals 7. And what does that mean? Okay, the y-axis, remember, is feet. So the ball starts at 7 feet in the air. And you have to think, too, you might be asking yourself, why did the ball start at 7 feet in the air? Well, the person who's throwing the ball is holding it. So if they're holding it, let's say she's 6 foot tall and she's holding it above her head, that's where the ball is actually starting from before it gets projected into the air. Alright, that's it for today, guys. If you have any questions, let me know. And good luck. Please take a look at the assignment.